Welcome back to statistics. Statistics are used in all walks of life, and we encounter them in everything from baseball games to opinion polls. And opinion polls, in particular, are probably the most face forward kind of inferential statistics that most people deal with. Um, think about, for instance, a presidential approval poll. A sample of individuals will be asked a very specific question that goes usually something like this: do you approve of the job the president is doing? And the sample will typically contain maybe several hundred up to 1,000 or maybe 1,500 individuals. And on the basis of that poll, news organizations will report on the president's approval rating. That is a kind of inferential statistics because in doing that kind of reporting, you're implicitly making an inference from a sample, like, out of 1,500 individuals surveyed, 43% approved the job the president's doing. You're making an inference from that sample to the larger population because you're saying that on the basis of the poll, we estimate that the president's true approval rating is, 43% plus or minus some margin of error. So, opinion polls are really sort of the prototypical example of inferential statistics that almost everyone is aware of. And we're going to talk about them in particular in this video. One of the things to realize about opinion polling, like a presidential approval poll, is that the data that's being collected from the sample is categorical. That is, the data that each individual contributes to the survey is a categorical answer. Do you approve of the job the president's doing? Yes, no, not sure. Any of those answers place an individual into a category, right? And what we're interested in when the data is categorical like this is typically the proportion of individuals in the sample and more generally the proportion of individuals in the population that would fall into a certain category. So, what percentage of individuals in the sample approve of the job the president's doing? And what does this tell us about the proportion of individuals in the overall population who approve of the job the president's doing? That's really the topic that we want to delve into today. So let's take a look and see what it shakes out. So, estimating population proportions. Uh, we're going to see the basic theory kind of take shape in the context of this example here. This is an example, a small part of a survey that was given to a sample of U.S. adults by the authors of this article. The article was entitled Believe It or Not, Religious and Other Paranormal Beliefs in the United States, and it was published in 2003 in the Journal for the Scientific Study of Religion. The overall point of the article was to try to identify associations between people's religious orientation and their sort of orientation towards paranormal beliefs of other kinds, like beliefs in ESP, for instance. But they also ask questions like the one you see here. Do you believe that extraterrestrial beings have visited Earth at some time in the past? And so this was one of the kinds of questions that was asked in this article, and we're going to focus on that to show how we can develop the ideas of a confidence interval for a population proportion. So it turned out that in this research article, there were 1,255 people who answered this question, and 442 of them answered yes. So that may seem a little bit surprising, but that looks like somewhere around a third of the sample stated that they believe that extraterrestrial beings have visited the Earth at some time in the past. And what we want to do is use this data to estimate the true proportion of all U.S. adults who believe that extraterrestrial beings have visited the Earth at some time in the past. Uh, Before going on here, I want to make a comment. I hope my tone of voice doesn't sound too skeptical here. Uh, the hypothesis that life might exist in places in the universe other than the Earth is not an outlandish one. Actually, a lot of scientists, maybe even most, would say that it's probably more likely than not that there are other places in the universe that harbor some kind of life. And of course, uh, the notion that life may exist in places other than the Earth is in no way contradictory towards other things that science tells us. After all, science tells us that life is a result of, various things on Earth, the chemistry, climate, and so on. But life is a natural process that could, obviously it could and did happen on Earth, and there's no scientific reason to say out of hand that it couldn't happen somewhere else. So the idea that that life might exist outside the bounds of our fair planet is certainly not unscientific. You can contrast this to other kinds of so-called paranormal or pseudoscientific beliefs, such as extrasensory perception. For instance, the idea that um, you know you through the power of your mind alone you can or some people have the ability to move physical objects, to like levitate and things like that. Those ideas actually sort of directly contradict what we know about the world, known physics, and so on. And so I think they're justly labeled as pseudoscientific. uh, Ideas about extraterrestrial life don't, contradict known science, although we still don't have direct evidence for them. It's certainly still possible, and so those kind of ideas are not pseudoscientific beliefs. Now, one could argue that, sort of getting back to our slide here, that it's one thing to say that life is possible on other worlds. It's quite another to say that you believe that extraterrestrial beings have visited Earth at some time in the past. That is certainly an extraordinary claim, and as we've discussed before, extraordinary claims do require extraordinary evidence. And it's fair to say that we don't have the kind of evidence that would be necessary for most scientists to conclude that it's definitely the case that we've been visited by extraterrestrial beings. But nevertheless, 442 people out of these 1,255 thought it was so. And so let's use this information to try to estimate the true proportion of all U.S. adults who believe that we have been visited by ET at some time in the Earth's history. So it's useful to go back and just kind of see where we are in the big scheme of things in terms of basic statistical concepts like population, parameters, sample, and so on. Our population here is the population of all U.S. adults. We're interested in finding out what proportion of all U.S. adults believe that ET has visited in the past. Our sample is our sample of 1,255 individuals discussed earlier in the survey. There is a statistical variable in play here, right? We could call that variable belief in extraterrestrial visits, and it is a categorical variable. It has three different levels: yes, no, and not sure. And these were the three values of a response that were recorded for these 1,255 individuals who took part in the survey. And again, we'd like to use this information to estimate the true proportion of all U.S. adults who would fall into the yes category. In other words, who would believe that Earth has in fact been visited by extraterrestrials. A little bit of notation and terminology kind of special to this kind of proportion problem. An observation is called a success if it falls into the category of interest. The category of interest is the category we're trying to compute a proportion for, right? In this case, it's the category of individuals who believe that Earth has been visited by extraterrestrials. And so an individual who fits into that category would be called a success for the purposes of this study. The proportion of successes in the entire population is the population parameter that we're interested in. And we're going to denote that parameter by the letter P. So lowercase p denotes the true proportion of all U.S. adults who believe we've been visited. But we're also interested in the proportion of successes in the sample, and we're going to denote that by p hat. So that is a sample statistic, and in fact, since p is unknown, we basically have to look to p hat as the best information that we have about p. So p hat is our sample statistic and our point estimate for p. Another bit of terminology, the number of successes in a sample is sometimes worth talking about, and we denote that number by the capital X. So these ideas are related. The sample proportion of successes is just the number of successes in the sample, that's X, divided by the sample size, which is N. And so the sample proportion, the number of successes in the sample, and the sample size are all related through this equation. In our example, our sample proportion was 442 over 1255, right? 442 answered yes to the question, and there were 1,255 in the sample overall. That turns out to be 0.3522. So our sample proportion is usually expressed as a proportion this way, not as a percentage, and you'll want to work with it that way. Of course, we could just as easily say 35.22% of the sample reported that they believed that extraterrestrials had visited the Earth. Okay, so we've got our sample proportion. It's our point estimate for the population proportion. Like any sample statistic, it has a sampling distribution. And so what are some of the basic facts about that sampling distribution? Well, the first one to be aware of is that the sample proportion p hat is an unbiased estimator of the population proportion p. That is, the sample proportion varies from sample to sample, right? It has some kind of sampling distribution, which we'll discuss in a minute. But the mean value of the sample proportion is precisely the population proportion p. So p hat is an unbiased estimator of the population proportion. We can also think about the standard deviation of the sample proportion. And that's given by this formula here. The standard deviation of p hat is the square root of the quantity p times 1 minus p over n. You'll notice the standard deviation here depends on p, the population proportion, which is usually unknown. So we'll usually have to estimate the standard deviation by the standard error. The standard error is just what you get when you plug in your best estimate for p, which of course is p hat, to the formula for the standard deviation. So the standard error of p hat is our estimate for the standard deviation of p hat. So we know about the mean of the sampling distribution, we know about the standard deviation of the sampling distribution, and we know how to estimate it using the standard error. What about the shape of the sampling distribution? Well, it turns out that the shape of the sampling distribution of a sample proportion is approximately normal. And this approximation gets better as the sample size gets larger. I'm going to show you a few screenshots here from a simulation in which basically I'm going to take repeated samples of size 1255 from the population, compute a sample proportion, and then throw that sample proportion into a histogram. So here I'm going to do that in one click 100 times. So there you see each dot represents a sample of size 1255, and the value of p hat for that sample is the value that's recorded. You can read it on the x-axis there. So for instance, that leftmost dot is just above 0.330. So there was a sample of 1255 that had a p hat value of just a little bit more than 0.330, and so on. So there you see 100 p hat values coming from 100 different samples, all of the same size, 1255. Let's throw 100 more in the plot, and 100 more, and 100 more, and 100 more. And so there's 500. And by just repeating this process, we're building up the sampling distribution. I'm going to throw actually 1,000 more into the histogram right here, and 1,000 more, and 1,000 more, and 1,000 more. Right now, there's 4,500 dots in our dot plot. Each dot corresponds again to a sample of size 1255, and you see the sampling distribution of p hat taking shape here. You can see that characteristic normal shape. In fact, it's a theorem. It's another result of what we call the central limit theorem, that the sampling distribution of p hat has an approximate normal distribution, and that approximation gets better as the sample size gets larger. So in summary, the story for the sampling distribution of our point estimate p hat is this: it's approximately normal, it has a mean that is the true population proportion p, and it has a standard deviation that's given by this formula here that we saw earlier. Since p is unknown, we usually have to estimate the standard deviation using the standard error. And this normal approximation for the sampling distribution is going to be good, going to be accurate, just in case you have at least 10 successes and 10 failures in your sample. So as long as you meet that criterion, it's safe to use this normal approximation for the sampling distribution of p hat. Okay, once we have a sampling distribution, we're basically off to the races. We can compute confidence intervals, for instance. And the basic story there is that a level C confidence interval for the true population proportion p is going to take the form of our point estimate, p hat, the sample proportion, plus or minus a margin of error, where the margin of error is given by this product of z star, a critical value from the standard normal distribution, times the standard error of p hat. Remember, that's our estimate for the standard deviation of p hat. And so this is a familiar story to us. Margins of error typically are products of critical values and standard errors, and that is no different in the case of a margin of error for a population proportion. Let's take a look at an example. Actually, let's look again at the same example we've been studying. Let's compute a 95% confidence interval for the true proportion of U.S. adults who believe that extraterrestrial beings have visited the Earth at some time in the past. And we'll base this on the sample data we've been discussing, those 442 who believed it out of the 1,255 in this survey. So we put together the pieces. The point estimate for p is our sample proportion p hat, which we've already seen is 0.3522. A critical value for 95% confidence just comes from the middle 95% of the standard normal distribution, and we've seen that number very often. That takes 1.96 standard deviations to span the middle 95% in a normal distribution. The standard error we compute by plugging in our p hat value to the formula for the standard error. So there you see it. Be careful with the calculations because you need to do the fraction first and then the square root. The result is that our standard error is 0.01348. So in other words, that sample proportion that we saw of 0.3522 varies from sample to sample with a standard deviation of about 0.013, right? So we wouldn't be surprised to see p hat values of like 0.36 or 0.34 and so on. The margin of error for 95% confidence is just the product of our critical value, 1.96, times that standard error. That turns out to be 0.02643. The 95% confidence interval for our true proportion then is our point estimate, p hat, 0.3522, plus or minus our margin of error, 0.0264. So that turns out to extend from about 0.3258 up to 0.3786. So in everyday language, we're 95% confident that the true proportion of all U.S. adults who believe that Earth has been visited by extraterrestrials in the past is between 32.58% and 37.88%. I was kind of surprised by that result. It should be noted that that survey data was from 2003. I'm kind of curious at the same time, a little leery of seeing how that data would change now in the age of social media and conspiracy theories galore. Who knows what that number would be now? It'd be an interesting subject to revisit. In any case, computing confidence intervals for a population proportion follows along the basic lines that we've seen in the past. That is, we take a point estimate, which is typically an unbiased estimator for our population parameter, and we add and subtract a margin of error, the margin of error being a critical value times a standard error of our point estimate. Okay, so that'll be it for now. We'll be talking more about sample proportions and population proportions subsequently. In the meantime, take care, and we'll see you again real soon.